The real-time pacer is a library for Simulink that can be found at this URL. This library is useful in order to speed up a simulation or in order to slow down a simulation when needed. The real-time pacer is a library for Simulink that is so useful in order to speed up a simulation or to slow down a simulation when necessary. It can be found at this URL. You can go to MathWorks and search for this name for the library. And it's useful both for Microsoft Windows and Unix systems. When I say Unix, I mean Linux or Mac OS operating systems. So we can, for example, put a speed up factor in this block that changes the speed of the simulation according to the CPU clock. We can put the simulation in real time. That's what we're gonna use in the next example. First of all, we must add the path to the MATLAB search path. You know, you must go to the Add Path menu, and then you must add the folder where the computer can find the real-time pacer. If you do that, the next time you open a model with a real-time pacer block, MATLAB will be able to use it. The real-time pacer folder contains all these files. First of all, an example in here, then the library, which is so important, and then these three M files that are the keystone of the library. Let's go now for an example I have built for Simulink, and I'm using the real-time pacer block with a speed up factor equals to 1. So that means that the simulation will run in real time. Here you can see that I have a block called elapsed real time that it's quite similar to the clock block in Simulink, but this tells us the real time of the simulation. As you can see, for further applications, I have put a gain in all those variables that are so interesting to me. As you can see here, first of all, the simulation time, then the error, the manipulated variable, and the process variable, both in volts and in centimeters. Because this is the feedback digital control loop of a two-tank system. Here, in this block, I have a two-tank system. I have an upper tank and a lower tank in here, and then water comes by means of a pump from the lower tank to the upper tank like this. And I'm interested in this level, the water level in the upper tank. So that's why I measure this water level in centimeters, and I get from the sensor its value in volts. The system is a nonlinear model because the output flow here, Q, is depending on the square root of the height of the water level in the upper tank, thanks to the Bernoulli equation. So that's why here I have a nonlinear model with a time delay. Here I have put a PI controller that guarantees that the error will be 0 in a long time. So at the end, on a steady state period, the error will be 0 thanks to the PI controller, thanks to the integral action of this controller. So let's now build a graphical user interface example for this MATLAB Simulink simulation model. First of all, we must type guide in the command window and press return, and then we are able to place several elements on a blank file. As you can see here, my graphical user interface can set a set point for the feedback control loop, can change the PI controller parameters, and then can monitor the signals, the process variable in centimeters, in volts, the control error, the controller action, and the simulation time in seconds in here. The graphical user interface can also start the model, stop the model, and quit the application, while here the variables set point, error, and process variable will be plotted. So let's first have a look at the graphical user interface object properties. If you double click on this, that is a static text element, if you double click, you can set the string that the user can see at the beginning once the application is open. Then you can define the kind, the style of element you are defining. For example, we can have a pop-up menu, we can have a checkbox, we can have an edit text, but now we have a text. That means that is a static text, so it will be for the information of the user. So then here I have a slider. This object is a slider, as you can see here. The style of the object is a slider, and its tag name is slider1. That tag names will be the names that I'm going to use to refer to these elements all along the code. So the user can change the value of this slider, and this tag name, all the functions associated with this tag name will do the actions that are connected with it. We will see later on. Now for the PI controller parameters, at any time the user will change the values of the PI controller parameters. But now let's have a look at the string by default. So when you open the guide, the graphical user interface, you will see a 10 in here. It's an edit text, as I told you before, and the tag name is edit KP, in order to refer to this element all along the code. Then what about the initialization and callbacks of the graphical user interface? Well, first of all, we must check the relationship between the graphical user interface that has both files, the .graphical user interface and the .m file. In the graphical user interface, we have the properties, and on the M file that is associated with this graphical user interface, we have the actions that these elements will do on the MATLAB environment. For this example, all the actions that this graphical user interface will do on the simulation model. So, first of all, let's have a look at the initialization of the model parameters. Well, by default, when you build a graphical user interface, here you have the name. The name is PSSP because it's the name of the course. Graphical user interface for two-tank system, definitive because it's the last version. And the opening function, you will see that it's the first function that is defined by default by MATLAB when you create a graphical user interface. It has, as you can see, several input arguments. I will have a look at this and this specifically. This H object is the name that you will refer to when in this function you must do something with this parameter, with this element. The handles, we will see later on, the handles are so useful in order to refer to any element of the graphical user interface. Afterwards, I'm going to show you an example. Well, first of all, when the function is opened, so when the graphical user interface is opened, this function is run by default at the beginning. So first of all, I open the model. The model is named closed loop with values, and then I use this function assign in the workspace vase, that is the basic workspace, the workspace that we all know when we define variables by the command window. I define a variable called setPoint, and the setPoint will have a value of 0. Why? Because the user will see that his element is 0. But this element is 0 in here, in the text box. But it has no effect on any variable in the command window, in the workspace, or in the simulation model. So you must assign at first this value in order to have this assignment in the workspace, because the user will trust that if here appears a 0, it means that the set point will be equal to 0. So maybe for the user this is okay, and the user will not change the slider. So then the user will trust that there is a value of 0 at the workspace. So you must do this at the beginning. So now what about when this is created? You can do the same assign in vase kp, and now kp between quotes, and then kp here a 7, okay? Because the user will see that the kp value is 7. So maybe the user agrees with this value. So the user will expect that this value is assigned in the workspace. So we have this way, that it's the same way that I did with the set point, but we have as an alternate way. Is this. Here, when you right click to this element, you can call a callback that is called the create function callback. And automatically MATLAB sets these code lines. So if you right click on this element, that it's an edit text, this is an edit text, because the user can edit this value. So if you right click on this, you will have a menu that has an option called callbacks. And then on every callback that is possible with this element, there is a callback called create function. This callback, this action, will run at the beginning when this element is being created. So what am I doing? I get the string value that I have defined with a 7 on the properties editor, and then I get for this object here, because I remind you that HObject is the way I have to refer to this element in the graphical user interface all along this function. So I get from this object the string value. So here I will have a 7 like this, but it's a character, it's a string, not a number. So then I must do the string to double this value in order to get a numerical value. And then I can assign to the workspace base kp this new value. Obviously, this way is shorter, but I'm only showing you that you can do the same thing in both ways. So on the opening function, you can define on the workspace all the variables the model will need to run, but instead of this, you can use the create function for every element in the graphical user interface and define there the value at the workspace by means of reading the string value you have defined on the property inspector. In other words, you can define the value that is present in this element by means of double-clicking, first of all, and go to the property inspector, put a 7 on the string field, and then copy and paste this code in order to define it in the workspace. The same I do with the edit ki, that's the tag name. This is the tag name of this edit text for the ki parameter of the PI controller, and this is the create function. So remember, right click on this element, then go to callbacks, and then go to create function, and automatically these code lines are created on the M file that is associated with the graphical user interface. Remember that when you have a graphical user interface application, you have a .gui file with all the elements, how they are distributed in the layout, and then you have these are the properties. Remember, these are the properties. Well, these are the actions. So when you right click on this element and you choose callbacks, you are choosing the actions. And which action is here? The create function. That means when you create this element. So when the graphical user interface runs, not for the first time, runs for every time you open it, you open the graphical user interface, this element is being created. So all the actions that are gathered here will run after the element is created. So then we have here the same as before, that is to get for this object, now it will not be the edit kp, it will be the edit ki, and I get for this object the string value. This string value is defined in the property inspector by simply double clicking this and put on the string field a 2 number. Then this new value does the following: only changes the string to a double number, to decimal number, and then this string, because from here we will get a 2, but by quotes, because it's a character, not a number, and then I change this string to double in order to get the new value, the numerical value. Then I assign this in the workspace base with to a variable called ki, this value. So I know you may think that this way of assigning the initial values for all the parameters is longer than this, but this way at the end becomes so simple, because if you want to change the value of the parameter, you just only double click on the property inspector, you double click with the left button of your mouse to the elements here, here, or whatever you want to change. And then you are expected only to change the string field. If you change this, because this is reading the string you have typed, you do not have to worry about the code, about the associated code. If you do this, you must open the code, find the line where you are assigning the value, and change the value directly. So I strongly prefer this way, despite it seems it's quite complicated, but at the end it's so simple, because you have no need to go again to the code in order to change the initial value for the parameter. The callbacks of the graphical user interface are the actions that are associated with every element within the interface. Let's have a look, for example, at this slider. Here we have a function that is called the slider1 callback, and we can define this action, this callback, by means of right-clicking the element when we are in the guide environment, and then on the menu we must select callbacks. Then in callback we have the create function and others, but among these others we have properly the callback. Then, as you can see here, this function has this and these input arguments I will refer to in a while. First of all, the age object will allow us to get some specific fields or parameters of this object. Here I use the age object in order to refer the own slider1 here within the function in order to get its value. So every time when the graphical user interface is running, every time the user clicks here or here, every time the user changes the value, this value is obtained, the number is obtained by this variable by means of this get age object, the field value. Then this value can be assigned to the workspace base to a variable sp that will have a value of value multiplied by 0.36, because the value will be in centimeters, but we want to get this value in volts, because at the end we have a control loop, so the set point, the process variable, and the error are in volts, because we are comparing the set point in volts and the process variable that comes from the sensor of the system. So that's why here we have value multiplied by 0.36, because 0.36 is for changing the set point into a voltage, because 0.36 is the sensor static gain, so this Ks. Then this is mandatory, it's very important. Every time the user changes something and we get this value, and then we assign this value in the workspace, it's very important, well, it's mandatory to do an update of the model. Because this way, when you set param the name of the model simulation command update, the Simulink model will stop briefly for a while. You wouldn't be noticed, but the model will check again all the variables, all the parameters of the model at the workspace. So this is very important, because this update will do the model to check the values of all variables in the workspace. Finally, once the model is updated, we can set this static text, the string that corresponds to the value in centimeters of the slider. So it's very easy, because we can set simply the string field, but we must translate, we must convert this value, this numeric value, into a string. That's why I use the num to string function. And pay attention that the tag name of this static text is text 17. So that's why I use the handles dot text 17, because the handles is the other input argument that's so interesting if we want to refer, to get or to set some value to a property of a different object than the object we are dealing in this function. So because this text has nothing to do with the slider 1, that's why I refer to text 17 by means of the handles object, not by means directly of the age object. The age object refers in this function to slider 1, while handles can refer to any object in the graphical user interface. Let's go now for this edit text. Is for the parameter, for the proportional parameter of the controller. As you can see, the input arguments are the same as always, age object, event data, and handles. And then what I do is to get the object string, the string value, this new string value must be converted into a numerical value. That's why I use the string to double function. So now I have a numerical value here, new value. So this new value is assigned in the workspace base to a variable called kp. If we only do that, the parameter of the simulation model will stay 7. It will not change. So this instruction here, the set parameter update of the model, is needed. This is mandatory. If we don't do that, the same as before, if we don't do this action, the model will not change the value of kp. The value of kp will be the original one. So we update the model in order to check the values of all the variables at the workspace and then to continue the simulation. Let's go now for this set of buttons, the start, stop, and quit buttons. For the start button is very easy. As you can see here, the callback, it only starts the model. So that's why set parameter, the name of the model without extension. Can you see here? The same as before, without extension, without extension. So that's the name of the file of the Simulink model. Then simulation command, but now it's not update, it's start. It's the same as if the user presses the play button in the graphical user interface in Simulink. Then about the stop button, we first assign a set point value of 0 at the workspace, because if the simulation is wanted to restart, then we will start from set point value of 0. That's in order to prevent unexpected values of set point if we restart the model. Then we update the model for this value to have an effect on the model as before, and finally we stop the model. For quitting is very easy. First of all, we close the model. That can be done by means of bd close, this instruction, and finally we close all open windows. Now we're gonna discuss about the listeners in the Simulink model. What are the listeners? The listeners are the objects that will take the values of every block that has been specified, and then all these values for the signals of these blocks will be sent to the graphical user interface by means of an updating file. So the listeners can be found or can be defined easily here in the model properties menu. Here we have the name of the model, and then we go to the menu, to the model properties menu, and here we have all the callbacks. This is the list in here, the list of all the callbacks that a Simulink model runs on every execution. For example, every time the model starts, so every time someone presses the play button, or we set param start, like in the previous slide, every time the model starts, these commands will be run. So first of all, you must copy this in order to show the graphical user interface handles, to make them visible. So in order for the listeners, in order to change the variables of all the objects in the graphical user interface. So first of all, you must copy and paste this line. And then we will define all the blocks which information is so interesting for us. Here we have 5 blocks, as you can see here: the error gain, the manipulated variable gain, the simulation time, and the PV in volts and in centimeters. So that's why I have defined 5 different blocks. As you can see here, we have the name of the model, we have the slash, and then the name of the block, error gain, MV gain, and so on. Then we will define what's the event. The event will be to post the outputs. That means that a block of this kind, this gain block, has an input and an output. This is so simple. The gain is 1. So what I have here is at the end what I will have here. So that's why the event will be to post the outputs. So the outputs of every gain block I have defined here will be informed, these outputs, to the graphical user interface by means of a file called update guide PSSP. So there will be a file called update graphical user interface PSSP, that is the name of the course. So this file will be an M file that I'm going to show you afterwards, that will send these values to the graphical user interface. And finally, I create the 5 objects which are called the listeners. The instruction is add exec event listener, and I define first of all the block, then the kind of event to post the outputs, and finally which file will be in charge of carrying the information, and will be update guide PSSP. So finally, how can we update this graphical user interface? By means of this file. Here you can see that update graphical user interface PSSP is the .m file that will be in charge to connect the simulation values in real time to the graphical user interface. So first of all, I create the RTO objects, the real-time objects. It will be by means of get param, not set param, get param of the model, and I put here the name of the model and then the slash and the name of the blocks. The blocks you remember from the preceding slides. These are the blocks which which am I interested in posting the outputs at the end, and then runtime object. Finally, I get the numerical values of the output ports of these objects, and I translate these numerical values into a strings. So that's why here you find number2string. So it's the real-time object. This real-time object is an object that has a field called output port. We have a single output port. Here we can put between round brackets 1, 2, 3 and so on, but we don't have more than one output because remember we have gain blocks, and then finally the data. So this numerical value in here will be translated into a string and saved in a variable. Then here I find the objects where I must copy or change their values by these strings. So first of all, I find an object with a tag name called static E. So that means that here on the graphical user interface, here at the beginning of the graphical user interface, here I have the objects of the process variable. This is the PB. This is the PB, but this is in volts, this is in centimeters, this is the error, and so on. So now, what am I doing? Am I searching for all these elements with the specific tag name I define? So we go back to this slide. So what am I doing here? Here I'm finding all these objects with a tag name called static E, MV, PV volts, and so on, because I want to post this data, well, this data but translated into strings, into this object. So then I can do a set of which object? This object in here. What is static text? Number one is the object that has a tag name called static E. So then I set the string field with str1. What is str1 here? The numerical value of this output port of this real-time object, but translated into a string. We will now see how it works. So as you can see here, I have the model, the SLX file. Then I have the fig file and the corresponding M file. Here we have all the properties of all the elements in the graphical user interface, and here I have the actions, the file for updating from the Simulink model to the graphical user interface, and we can, for example, run the graphical user interface by drag and drop the M or the fig file. As we can see here at the beginning, the model has been opened, and then the graphical user interface appears. Let's now minimize the model in order to check that the variables in the workspace are defined by default. Now in this case, KP is 10, KI is 2, as you can see here, and SP is 0. Let's, for example, change the value of the set point. Here, as you can see, we have 3.0216 in centimeters, but in volts we have 1.09. Let's change, for example, the parameters of the controller. Let's say that KP can be 18. As you can see, when I press the enter, the 18 appears here. And then let's say that this is 5, for example. Now we can start the model and we will see that the simulation will run. This is real time, 5 seconds, 8 seconds, and you can see here that the error at the beginning was equal to the set point, and now the error, as you can see here, is decreasing, while the process variable is increasing. While the model is running, we can, for example, change the value of the set point. Let's say that now the value is this, and you will see that then immediately after the set point has changed.